We haven't looked at this. We're going to look at what we call a random variable and what a probability distribution is and expected value. Okay, so the first thing I want to look at is we'll kind of go through what we mean by a random variable here. All right, so when we look at a random, gosh, what in the heck? Okay, for some reason it messed me up and went to another page. Everything's a surprise on this program. Okay, so a random variable, what this is this is just a function that assigns a numerical value to each event in the sample space. So it's a little bit different idea. So I'm going to use this example to just explain something that we've already seen before. So the idea is if you tossed 3 coins, there's 8 possibilities. Okay, again, we know that when you toss a coin, 2 things that can happen. But if you toss it 3 times, 2 times 2 times 2 would be 8. So there's 8 outcomes when you toss 3 coins. We already know that. All right. And these are this is the sample space. So you would have like a tail, 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 head, and so forth. Those are the 8 outcomes you would get if you went to a probability or a tree diagram if you did that. Okay, well, what we're going to do on this is we're going to look at defining the random variable this way. So a random variable is what it's going to be is it's going to be something that represents a number. So in this case, it represents the number of heads. Okay, so the possibilities is when you toss 3 coins, you could either have 0 heads, 1 head, 2 heads, or 3 heads, right? Okay, those are the possibilities. So this right here, tail, 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 would mean you have 0 heads. Okay, these 3 right here are going to mean that you have 1 head. Okay, so there's just 1 head and those 3 right there. So that's how that matches up. And then this one has 2 heads. So there's 3 possibilities that have 2 heads. And then finally, the last one has 3 heads like that. So what we're doing is we're looking at the number of heads we have. We call that a random variable. So the variable x is going to be either 0, 1, 2, or 3. Is everybody with me so far? Okay, it's how many heads we have. So it's 0, 1, 2, or 3. There's nothing else possible. So here's what we do on this then. So we're going to do the probability of 0. Now that means 0 heads. It doesn't mean we're going to toss 3 coins and a 0 pops up because that's impossible. It's how many heads we have, okay? Right, so 0 heads would only be this one possibility right there. Okay, that would be you get all tails, so that would be a 1/8 probability like that. Okay, that's the idea. Okay, the next one is the probability of getting 1 head. So how many possibilities are there where you flip the 3 coins and just 1 head pops up? There's 3. Those are the 3 that I highlighted in blue. So this probability would be 3 out of 8. Okay, that's just getting exactly 1 head. That's the blue. Okay, the next one is the probability of getting 2 heads. So how many possibilities are there for getting 2 heads? It's 3 also. That's the yellow ones. Okay, 2 heads, 2 heads, 2 heads. So that's also 3/8. And then the last one is the probability of getting 3 heads. So how many possibilities there? 1. So that's 1 out of 8. Okay, does everybody understand what I'm talking about? Okay, this is what we call a random variable. So it's just the probability of no heads is just this one, 1 out of 8. The probability of 1 head would be this, or this. So that's 3/8. Probability of 2 heads is this, or this. 3/8, and so forth. What are these 3 numbers? What are these 4 numbers add up to? That's important. Add up to 1. Okay, that's the total probability is 1. So one thing that you want to notice on here too is you want to write this down just kind of as a note to yourself. So if you add all of these individual probabilities up, you should get 8/8 or you should get 1. Okay, that's what should happen when you do that then. Okay, so on our random variable, we're defining that to be a number of whatever occurs in the problem. So that would be the first idea I want to show you. Okay, any questions about that? Okay, we call that a random variable when we're letting it be a number of some event happening. Okay, so what we'll do on this, I've already showed you if you add the probabilities on this, you're going to get 1, so you'd expect that. Now, the next thing I want to do is I want to show you, I'm just going to go over this thing that we call a histogram. And this is a way to represent visually which things are the most likely and which events are the least likely, okay? So with this one, what I'm doing is the number of heads, there's a 1/8 probability for getting 0 heads. There's a 3/8 probability for 1 head, a 3/8 for 2, and then a 1/8 for 3. So all this histogram is saying is it's just saying that's the probability for each outcome. No head, 1 head, 2 head, 3 heads. Okay? So what's the most likely thing to happen on this problem? We'll get 1 head or 2 heads, right? That's highly likely, and those things at the end are less likely. So a lot of times, and you guys probably, a lot of you, if you're a business major, you probably will take business statistics at some point. That kind of looks like a bell-shaped curve. That happens a lot of times is the highly likely events are kind of clustered in the middle, and the least likely events are out there at kind of at the edges like that. So that's what a histogram is it's just visually a way to look at the probability. All right, are you guys okay so far? Okay, it's just a different way of looking at the problem with numbers. So we're going to kind of use this to get what we call expected value ultimately on this, okay? So a couple of things on the next page is what we're always going to do on our random variable is we're just going to name that usually with the variable x, okay, like I have there. And that probability, like we've already learned, is going to be between 0 and 1. 1 is a certain probability, 0 is impossible. All of the individual probabilities should always add up to 1. That's what that second statement is saying. So what I did on this one is, this is just kind of how you would do a probability distribution for rolling 2 dice. Okay, so remember, when you roll 2 dice, there's 36 outcomes because there's 6 things that can happen when you roll 1 dice, 6 things for the second, 6 times 6 is 36. Now we've already done this kind of stuff right here, so these are the sums. So what we're doing on this is the smallest sum would be 2. You can roll 2 dice and get a 2, right? What's the biggest sum you can get? 12, okay, like that. All right, so these are the sums of the dice, and what I'm doing is just showing you the possibilities. There's one way to get a sum of 2, so that would be a 1 out of 36 probability, which you could change to a decimal if you wanted to. There is 2 ways to get a sum of 3. You either do a 1-2 or a 1-3. So that's probability. This would be all the possibilities to get a sum of 4 and so forth. So what's the most likely thing to happen when you roll 2 dice? You get a 7. Okay, that's highly likely. The least likely is a 12 or a 1 right there. Okay, so that what's happening is, again, the histogram a lot of times will kind of cluster in the middle is where the highest probabilities are. Now, if you added up every one of these probabilities, what would you get? You would get 1, okay? Now, these are represented in terms of decimals, so that's what that probability histogram would look like then. All right, does that make sense? Okay, the random variable is the sum of the dice can either be 2, 3, 4, 5, 6, 7, all the way up to 12. So that's that random variable. It's a numeric value like that, okay? So the way that you would name this is you would say like this, you would just say x equals the sum of the 2 dice. Okay, and then again, the possibilities on this, we would just say x is, and you don't have to write all this out, 2, 3, ... all the way up to 12. Okay, so that's it. All right, so what we're doing is we're getting a numeric value when we put that together then, okay? All right, so now what we're going to do is kind of begin to put this together. This next problem right here is we're going to look at the kind of go back to doing a deck of cards. And with this problem, it says 3 cards are drawn from a deck, and the number of kings are counted. So we're going to make a probability distribution and a histogram. So the first thing we want to do is we want to define this random variable. So the first thing is, whenever you draw cards, are cards a combination or a permutation? In other words, does order matter or does order not matter? Order does not matter, so it's what? It's a combination, okay? So that's kind of an important thing when you're dealing with cards. Doesn't matter what order you're dealt the cards. So order does not matter. Okay, so that means we're going to deal with combinations. So we're going to deal with some combinations when we're doing this then, okay, like we've learned. Okay, the second thing we're going to go ahead and do is we're going to go ahead and define our random variable. I always use X for the random variable. Now, according to the problem, it says the number of kings are counted, okay? So you draw 3 cards. Okay, what are the possibilities for kings? You could get 4, what else? You could get 3, you could get 2, you could get 1, or you could get no kings, right? Okay, now you're only drawing 3 cards, so you couldn't get all 4. So basically, you would go like this. X is going to be the number of kings, so you want to write that down. And in this problem, since we're only drawing 3 cards, we would say X is an element of this set. You could either get 0 kings, 1 king, 2 kings, or 3 kings. That's because we're doing 3 cards. So nothing else is possible, correct? You draw 3 cards and you're either going to get no kings, 1 king, 2, or 3. That's it. Everybody with me? Okay, that's the random variable. And again, that represents a number on that then. Okay, so what we're going to do next is we're going to crunch out the individual probabilities. So what we're going to do is we're going to do the probability of 0, which means no kings. Okay, so this is where we got to do the combination stuff, all right? So it kind of goes like this. Now we were working on this quite a bit last time, and when you're doing a probability, remember we're drawing 3 cards, so it goes kind of like this, okay? The bottom, how many cards in a deck? 52, and you are choosing 3 cards. Now I usually write the combination like that. You can also write the combination like 52-3. I don't care which way you do it. I just usually use the parentheses for a combination like that then. Okay, so let's see. So the next thing we're going to do is this. What goes here? This is where you have to think about it. We're going to do a combination, and we're not going to get any kings at all. Okay, so think about this. How many of the cards are not kings? In a deck of cards, how many are not kings? 48, right? So there's 48 cards that are not kings. There's 4 kings in a deck. So you're going to choose those 3 cards from the 48 that are not kings. That's how I figure that out. Does that make sense? If you get no kings, that means you drew out of the 48 cards that are not kings. Now, a lot of these things I went ahead and worked out. I don't want to take a lot of time. I've already taught you how to put this in your calculator. So this one turns out to be 0.7826. All right, let me ask you a question. If you just drew 3 cards out of a deck, that is saying 78% of the time you're not going to get a king. Is that logical to you? It's only 4 kings in a deck, so it's not very likely that you're going to get a king. Is that logical to you? All right, okay, you're going to think about these probabilities as we go through this then. Okay, next thing we're going to do is we're going to do the probability of getting 1 king. Okay, and this, you got to be kind of careful when you do this then. So the probability, you're going to have the denominator is still you're choosing 3 cards out of 52. Okay, all right, now what you have to do on this, now this you got to be kind of careful about. All right, you're going to pick a king. So I'm going to put a 1 there. How many kings are in a deck? 4, okay? So that basically, that 4-1 represents that you chose 1 king out of the 4 cards that are kings, okay? Now, pay attention to this carefully. This is where students kind of struggle. So I've got 1 card. That means I got 2 other cards to choose, right? Okay, so I got that. So how many cards in the deck are not kings? I already asked that question. 48. Okay, so what you have to understand is you have to understand this. Okay, this basically means we got 1 king. We chose 1 from 4. 2 other cards are left over since we're choosing 3 cards out of the cards that are not kings. Does that make sense? Okay, you got to get that put together. That's usually one of the difficult parts of these problems for students on combinations is putting that together. Okay, now what I'm going to do is I did this on my calculator already. So this is 0.2042. So about 20% of the time, you would, if you drew 3 cards, you would get a king. Okay, it's, not that likely, but it's not like highly unlikely. Okay, somewhere kind of in the middle. Okay, now we're going to move on to getting 2 kings. Okay, like this. Okay, and let's see if you guys can put that together. Okay, I never know how well students really understand the combination stuff. So let me see if you can figure this out. Okay, in the previous problem, 1 king was 1 from 4. So what would 2 kings be? 2 from 4. How many cards are left? 1 out of what? 48. Okay, good. Okay, so it goes like that. You got to understand what all these numbers are saying. So there are 2 kings selected from the 4 kings in the deck. You have 1 leftover card out of 48 that are not kings. Okay, do those numbers make sense to everybody? Okay, 2 from 4, 1 from 48. Okay, now if you work that out, this is less likely. So you're less likely to get 2 kings. When I did this, let's see, on this one I got 0.0130. So about 1.3% of the time, you would get 2 kings. Okay, that's highly unlikely. Okay, now let's do the last one. So remember, we're only drawing 3 cards, so it's basically going to go like this then. Okay, so let's see if we can figure this out. Okay, so with this one, again, 52-3. Okay, what do you think is going to go in the numerator? All of the cards I choose are kings this time, so what's that going to be? How many kings? There you go, 4-3. You're choosing 3 kings out of the 4, like that. So that one goes like this. Okay, so this gets put together like this. There's 4 kings in a deck. You chose 3. Okay, yes. Am I doing what? No, I'm multiplying. And that's a real good question. You're talking about right here, right? Yeah, you're multiplying when you do that. Okay, for every possibility, there's all those other possibilities, so you're multiplying. Okay, so what happens on this one then, this would be the least likely event. So I went ahead and did this on the calculator and I got 0.002. Well, that's like 0.02% of the time you would reach into a deck and get 3 kings, okay, out of your 3 cards, okay? So what's happening is the probability is changing like that then, all right? Okay, so that's kind of the idea with that. That's the third thing we're going to do. Now, the other thing I want to ask you is this, okay? What do you think these 4 numbers add up to? Add up to 1, right? Okay, 78%, 20%, 1.3, yeah, they all add up to 1. So you can check and see if you've done that correctly just by quickly adding those up and see if they add up to 100%, which they should. So the next thing we're going to do is what we call a probability distribution. Go ahead.
You divide in the top, 4 divided by 1, 48 divided by 2, and then multiplying.
Okay, like what I'm doing on the calculator on this is you can do that combination in your calculator, and that's what I'm really doing on that. So for instance, on the probability of 1, let me show you what I did on the probability of 1. So what I do is I go parentheses, I go for math, probability, combination, and then that was 1 at a time like that. I'm doing the second one like that. So I do that, then I multiply, so you can do the multiplication symbol there. Then it would be 48-2, so I go 48, math, probability, combination, taking 2 at a time. So you can do all this in one step on your calculator like that. And then you divide by 52, and then same thing, math, probability, and then that is 3 cards like that. Okay, so that's what I did. I just did that outside of class, so I don't have to take all that time to do that then. Okay, so when you're doing those combinations, all I want you to do on your paper is write down the formula like I've done, then go to your calculator and crunch it out. Okay, everybody remember that okay? Okay, so that's where you do your combinations, is make sure that you know how to do that on your calculator for your test next week. Okay, so the probability distribution is going to go like this. So we're going to make a chart, and we've already kind of figured this out. So this is going to be the number of kings, and then this will be the probability. So I'm going to call this just P of X. Okay, that stands for the probability. So the possibilities were no king, 1 king, 2, or 3. And then we already got those probabilities. So this probability was 0.7826. This one was 0.2042. Then 0.0130. And then 0.002 like that. So we called that a probability distribution. And again, that second row should add up to 1 like that. Okay, you guys with me? Okay, now we're going to do a histogram. Okay, so if we do a probability histogram, you want to do this like this. Right? What we're going to do is we're just going to, kind of draw out the possibilities. We could have 0, we could have 1 king, 2 kings, or we could have 3 kings. Okay, that's what that part represents. That's your random variable. That's the x-axis. Now your probabilities, we're just going to do percentages like this. So let's kind of go like this. The highest percentage we got was like around a little bit over 75. So let's just kind of go like this. 0.10, 0.20, and so forth like that. 0.30, these are the probabilities. You can just put 0.1, 0.2, 0.3, so forth like that. And it doesn't have to be perfect. You just want to get everything put on there and kind of estimate how that goes. Okay, so that would be your probabilities. So what you do when you graph this out is you go like this. So the probability of getting 0 kings is 78%. So you draw a bar and you just estimate that thing is going up to about 0.78, like that. So you just do the bar for your histogram like that. Okay, that would be your first one, would go like that. Okay, so that's the most likely outcome like that. Then what we're going to do is we're going to do the 1 king was about 20%. Okay, so on this one, you just do a bar that's up to about 20% like that. Again, it doesn't have to be perfect, just kind of estimate and get that put together like that. Okay, so that would be that. That's the second most likely outcome. Then the other ones are so tiny you'll hardly even see anything on them. So this one is like 1%. So I'll just kind of do like that. Okay, that's not drawn to scale, but that's good enough. So that's 1%. And then the very last one would be just, it'd just be like a line practically. Okay, like that. So that's what your probability histogram is saying, it's saying the probability of no king is about 78.78. This one is about 0.20. That's about 0.013, and then that's just barely even there, okay? So what that says, and like some of the examples we're going like this, with the high probability in the center, not on this one, the highest probability is here, okay? So it's kind of decreasing in probability like that. Okay, does that make sense? Okay, so we crunched out all the probabilities with the possibility of numbers of kings. That's the probability distribution. It's just like a table, and then that translates into a histogram. Purpose of that is it's real clear visually that that's the highest probability on that, okay? That's the purpose of graphing a lot of times, is to visually see what is represented by your data. All right, any questions about anything so far? Okay, we good? Okay. All right, so we're going to kind of look at expected value as the big thing that we look at in this section. And I'm going to show you how this expected value formula works, and then kind of what it does for you. Okay, and what will happen on these is you have some sort of a probability distribution, and you're trying to crunch out what you're expected to get. Like on the last example, you would be expected to get no kings, right? Okay, and I'll tell you what would happen if we did the expected value on this. The answer would be somewhere between 0 and 1. Okay, it would end up being, and what we do with expected values, it's kind of like on the average, how many kings do we get? Well, we don't get 0 every time, but we get mostly a number close to 0. So the expected value is just kind of a ratio of all those numbers. We expect to get a number close to 0 on that problem. All right, so let me show you on this next page how you crunch out expected value. The formula, when you have a probability distribution like this, what you end up doing is this is your random variable and this is your probability. You just multiply these numbers and then you add up the results, and that gives you what we call an expected value, okay? So I'm going to go down and do this probability distribution, and we already did this earlier in class. This is just the number of heads. So the probability, this is basically you're tossing 3 coins like we did earlier. So the meaning of this stuff is the probability of getting no heads is an 1/8. The probability of getting 1 head is 3/8. Probability of two heads is 3/8. Probability of all heads, 3 heads, is 1/8. Okay, so what happens on this is you would expect the answer to be somewhere in the middle. Okay, so here's how you do the expected value. So what you do is you write down E of X. That's the notation for expected value. And what you do is real simple. You just take those 2 numbers and you multiply. So you do 0 times 1/8. Then you do the same thing here. You do 1 times 3/8. Then you do the same thing here. You just add these things up. So that would be 2 times 3/8. And then the last one you do is you do plus 3 times 1/8 like that. Okay, so that's the arithmetic you do. Most of the time you're going to do this on your calculator. So this is going to be 0 there. That's going to be 3/8 if you multiply that. And remember, you just go straight across on these things. So that would be 6/8. And then this would be 3/8 like that. Okay, now you just go ahead. They already all have a common denominator. So what you would end up getting is this would be 12/8 like that. And then you can go directly to your calculator if you want to and just do it from there. You don't have to reduce the fraction. These expected values, I'm always going to have you just get decimals. So if I go 12 divided by 8, that expected value is about 1.5. So, and I'll explain what we mean by that expected value. Okay, so that's 1.5. So again, what you do is if you have a probability distribution, you do that times that, multiply and then add the results. So the mathematics of that's easy. You guys follow what I did there, okay? Now, here's what this means, okay? On the average, and I want you to tell me if this makes any sense to you, okay? The 1.5 means how many heads are you going to get? Okay, so if you tossed 3 coins an infinite number of times, that doesn't mean you would get 1.5 heads. It means on the average, that's how many you would get. So is that logical that it would be halfway between 1 head and 2 heads? I think the probabilities are the same. So basically all it's doing is, on the average, what's the most likely outcome? The most likely outcome is halfway between 1 and 2. Does that make any sense? Okay, so that's the idea, is that's the expected value on that, is you would get 1.5 heads. Okay, does that make any sense? Okay, that's the value. It doesn't mean that you're going to get 1.5 heads. That's impossible, but that's how many you're going to get on the average. Okay, so that's the expected value. Okay, so I'm going to work a little bit more with this. Expected value is actually pretty easy if you have a probability distribution. So let's do this one. Let's see, down kind of at the bottom here. Okay, so on this one, okay, this says, what is the expected value or the long run average of the number of dots facing up for the roll of a single dice? So what we're going to do is we're going to make a probability distribution on this problem then. So we're only rolling 1 dice. So here's kind of what happens on this. So what we're doing is it's the number of dots facing up. Okay, so it goes like this. We're first going to write down kind of what our variable is. X is the random variable. It's the number that shows up on the dice. Okay, so how many possibilities are there if it's a six-sided dice? There's six things that can happen, right? Okay, so basically this random variable would be an element of these things, okay? What's possible is you either get a 1 showing up on the dice, a 2, a 3, a 4, a 5, or a 6. Okay, those are the possibilities that you get, okay? Now what we're going to do is we're going to do a probability distribution table to get this put together, all right? So what you want to do on your probability distribution is you're going to have X, so that's the number on the dice, and then you're going to do the probability of that happening, okay, like that. So the possible outcomes are going to be you get a 1, a 2, a 3, a 4, a 5, or a 6 like that. Okay, so always list out, like on the previous problem, I listed out what the possibilities were for the number of kings. Okay, so what's the probability of rolling one dice and getting a 1? 1 out of 6, right? What's the probability of rolling a dice and getting a 2? 1 out of 6 again. Isn't all these probabilities the same? Probability of getting a 3 is a 1/6. So they're all the same. And what will happen is notice that these 6 numbers, don't they all add up to 1? Okay, that will always happen in your probability distribution. That would be the total probability to be 100%. So here's what you do to do the expected value. And doing it's real easy once you have that probability distribution done. What you do is you just do this. You do 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6 plus 4 times 1/6. Some of this stuff you can do in your head, plus 5 times 1/6 and plus 6 times 1/6. Okay, and what I like to do is just do whatever I can, as much as I can before I go to the calculator. All right, so basically you're just going to work out these 6 arithmetic problems, and then we can go to the calculator. We'll end up getting a decimal. Although this one's going to turn out, I already know kind of where this one's going to turn out. Okay, so this is going to be 1/6 plus 2/6 plus 3/6 plus 4/6, multiplying fractions straight across, plus 5/6 plus 6/6. Okay, so they all have a common denominator. And let's see, if you add those numbers on top, that looks like that would be 11, 15, 18. That should be 21 out of 6. Okay, then you could take your calculator and go ahead and get to a decimal like this. And let's do that, and let's think about whether this makes any sense. If you understand expected value, you could do this problem in your head. Okay, so the expected value is 3.5. Okay, does everybody see what I did with my calculation? Okay, is it logical that the answer to this problem is halfway in the middle of 3 and 4? Yeah, absolutely. All these probabilities are the same. So on the average, if you rolled dice, on the average, that's what would end up happening, is you would end up getting a number showing up between those two right there. It's like halfway in the middle like that. On the average, that's what you would end up getting. Okay, all right? So that would be the idea with that. It's just kind of right in the middle. It's doing an average of those possibilities like that. Okay, so that's it. All right, does that make sense? Okay, all right, tried to give you a couple of examples that are pretty easy to interpret. Like this last one, 1.5 was like halfway in the middle. That's like halfway in the middle of your histogram. Same thing happens there, okay? But it depends on the situation. It doesn't always work that way. Okay, so this is what I want you to try to do. And I want to give you a few minutes to see if you can do this. You want to get your calculator out, and you want to do the expected value. I've already given you the probability distribution, so you want to do this like this, okay? And I'll just give you a minute to see if you can do it. Don't wait for me. I want to give you a little time to put this together. All you do on this expected value is you do this. You do 0 times 1/16 plus 1 times 1/4 plus 2 times 3/8 plus 3 times 1/4 plus 4 times 1/16. So you want to write that out on your paper and then go to your calculator to get that final answer on that. And Same thing with this one, you're going to do 0 times this, plus 1 times that, plus 2 times that, plus 3 times that. Okay, so go for it and take a few minutes and see if you can get that put together. Get your calculator out and see if you can get those okay. And then when you get an answer, it's usually not a bad idea to kind of think about, you know, whether your answer makes any sense to you or not.
You gotta find the common denominator, right?
You can go straight to your calculator if you want to, because you're going to get decimals on these anyway. So you don't have to necessarily do that unless you want to. I'd just probably be inclined to multiply out and then just go straight to my calculator is what I'd do. Now I'd probably multiply the fractions out, but then I'd just go straight to the calculator. What have we got on the first one? 2. Is that a logical answer? Yeah, remember it's like an average on that. Okay, so again, you know, I would just sort of put this in like this after I get everything calculated. You don't have to worry about getting a common denominator and everything. It's just put in 1/4 plus 6/8 plus 3/4 plus 4/16. Don't even bother with the common denominator and reducing fractions because I want that anyway. So the expected value on this one is 2. And to me, notice these things are kind of symmetric. And it's because you have 1/16 and 1/4. So that's what's the most highly likely. So that would be, if you did the histogram, it would be symmetrical like that. So the high point, the most common outcome on the average, you're going to have 2 if you average up all those. So basically, if you tossed 4 coins on this, basically 2 heads would be what comes up most often on the average. That's what that means. Okay. The next one, you should have got 0.2308. So again, I just did this calculation. That's 0. And I just put it in my calculator. I just did 0.2042 plus 2 times 0.0130 plus 3 times that. Okay, so that expected value would be 0.2308. Well, okay, where does that fall? In the grand scheme of things, 0.23 is between 0 and 1. And it's closer to 0. The reason it's close to 0 is because that's the highest probability, right? Okay, so this one is symmetrical. That's why we got 2. This one skews itself towards the highest probability. Does that make sense? So if you get an answer to these problems, look at your table and see if it's logical to you. Okay, that's important that you do that. Okay, so if the table is given to you on expected value, then you just got to know the formula and what that value means. So is there any question on anything? Everybody okay? All right. Okay, so let's see. Now the next thing I'm going to do is just take a scenario and see if we can put this together. So we're going to do expected value on this example. So let me read the problem, and then we'll try to do, usually once we get the probability distribution put together, then it's pretty easy to find the expected value. Okay, so this one says you have a carton, you have 20 laptop batteries, contains 2 defective ones. A random sample of 3 is selected from the 20 and tested. So the key thing it says right here is X is the random variable, and it represents the number of defective batteries. Okay, so we're going to write this, kind of start like this when you do the problem. Okay, the variable X is going to represent the number of defective batteries. And then we got to define what that would be by reading the problem. We got to define what that set is going to be. Okay, so we need to figure out what are the possibilities on this. Okay, so basically the problem says this. Okay, it says that you have 20 batteries and then there's 2 defective ones. Out of that 20, 2 of them are defective. So you're going to randomly reach in and you're going to grab a battery. So what are the possibilities? You could get what? 0 defective batteries. Are you supposed to grab 3? Oh, you are supposed to do 3. I'm sorry. Okay. Same idea though. You're going to randomly reach in for 3 batteries. What are the possibilities of them being defective? 0, right? Okay, you might get no defective. What else? You could get 1 defective. What else? 2. Can you get more than 2? No. Okay, because there's only 2 in there. Okay, it says there's 2 defective batteries. So that means when you reach in to grab your 3 batteries, you're either going to get no defective ones, 1 defective one, or 2 defective. So you want to know what those numbers mean. That's just the number of defective batteries. Okay, and there's nothing possible because there's only two in there anyway. Okay, all right, so we're going to figure out what is the most possible. Let me ask you this question. There's 20 batteries, 2 of them are defective. So if I said expected value, what would you expect it to be closer to, 0, 1, or 2? What do you think? 0, exactly, because most of the batteries are not defective, right? Okay, so our expected value is probably going to be between 0 and 1, closer to 0, because there's 20 batteries and only 2 are defective. So our expected value ought to be, most of the time, we're not going to reach in there and get defective batteries. That's the idea. Okay, so what we want to do next thing is we want to go ahead and we want to crunch out these probabilities. So we're going to do the probability of reaching in and getting 0 defective batteries, the probability of getting 1 defective battery, and 2. Okay, now here's the thing you got to think about on this. All right, the thing is, you got to ask yourself the question, does order matter or does it not matter? Okay, the idea is you're going to reach in there and get 3 batteries. Does it matter which order those batteries are in? No, it's just like cards. So if order does not matter, then what is it? Combination or permutation? It's a combination. Okay, it doesn't matter what order they are that they're in. It's still, you're going to count how many of the batteries are defective or not. Okay, so the way this would go is it would go like this. So we're going to do a probability. This is just like the card thing I did, except this time you're selecting 3 batteries from 20. Okay, that's what the problem said, is there's 20 batteries and you're choosing 3. Okay, all right. Now on this one, you got to be kind of careful on the 0. So how many batteries? Now you're going to choose 3 batteries. So how many of those 20 batteries are not defective? What? 18, right, okay. So that's going to be this. That's going to be 18. You're going to choose 3 from 18. That 18 are not defective. So we're doing the probability of 0 defective. So the 3 we choose are going to come from that 18. Okay? Now let's see if I work this out. I worked this out and that gave me 0.716. You do that on the calculator like I showed you earlier. Okay? Now what we're going to do is we're going to go to one defective battery. Okay? And again, the denominator is a combination of 20, choosing 3 from 20. Okay, now this is where you got to be careful on this. We're going to choose one defective battery. So what do you choose that from? What is that number right there going to be? 2. How many defective batteries are there? There's 2. So you're going to choose 1 from 2 like that. Okay, just think of this just like you do the cards. Okay, how many other batteries do you have to choose? You've already chose one bad one. Now you got 2 left over, right? Okay. How many good batteries are there? 18. Okay, so that's how that goes. You got to understand the thought process is I chose one of the 2 bad batteries, and I chose 2 of the good batteries. I chose 3 batteries, so 1 plus 2 is 3. Does that make sense? Okay, so you got to reason that out the same way you do the cards. And then if you do this on your calculator, let's see, when I work this out, I got 0.268, like that. Okay. All right. So now the next one, we're going to get 2 defective batteries. Okay. So it goes like this then. All right. We still have that. Okay. What am I going to go on this one? These are 2 bad batteries out of how many? 2. There's 2 bad. So that's 2, 2. What's going to go here? 18, 1. There's 18 good batteries, and you're going to choose 1. So if you choose 2 bad batteries, then the other one has to be good. Okay, so it's going to be, this is 2, 2, like that. Okay, there's 2 out of 2. 18, you're going to choose 1 like that. Okay, when you do that, crunch that out on your calculator, you should get 0.016 like that. Okay?
Can you show us that one time?
Which one?
Can you go through that problem one time when you calculate?
Oh, on the calculator? Yep. Okay, you just got to do it, put in exactly this. You got to use parentheses generally when you do that. So if I did the last one, for example, you would go like this. You go parenthesis 2, then math probability, option 3, and then 2 like that. And then you do times. You can leave the times off of there. If you use parentheses, the calculator will know what you're doing. Okay, then I go 18, and then math, again, probability, option 3 for combination, 1 at a time. Okay, like that. Okay, and then divide by the 23, so you go like this. So it's just a matter of knowing where the buttons are and how to use your parenthesis keys. The safe way to do this is always to just use parenthesis keys when you do that then. Okay, so that gives the 0.016. Okay? Okay? Yes. Okay, so we got that. Now, does it make sense to you guys that the highest probability is that you will get no defective batteries? Yeah, there's 20 batteries and only 2 are defective. So that's the highest probability. The probability of getting 2 defective batteries is real low. Okay, because there's only 2 out of the 18, out of the 20 in there like that. So what we're going to do now is we're going to do the probability distribution. So you do this like this. Okay, first of all, this would be number of defective batteries, and then this would be the probability of getting a defective battery. So we just crunched out that the probability of getting 0 defective batteries is 0.716. The probability of 1 defective battery is 0.268, and then the probability of 2 is 0.016. So you want to get that probability distribution so that you can easily figure the expected value. So the expected value should be close to 0 because that's the highest probability. So what you do on the expected value is you say E of X, just like I showed you before, you go 0 times 0.716 plus 1 times 0.268, and then plus 2 times 0.016 like that, And you can do that on your calculator. Of course, that goes to 0. So you might want to check me on that then. I think I already worked that out and got 0.3. And that's logical to me, is that it's somewhere between 0 and 1 because that's the highest probability. It's closer to 0 than 1 because that's a high probability. What's that? Which thing?
That slash right there, 0, parentheses.
No, it's because if you're multiplying by 0, it's 0 times 80.
Oh, that thing right there is just 0. Okay, so what I did was when I was saying, okay,
Oh, you crossed it out. Okay, I got you.
Okay, so then just cross that out.
No, I thought
Okay.
you had a new sample. You didn't.
Yeah, no, I got you. That's it. Okay, so that's how you would do the expected value. That's how you put that together. Hardest part of this problem for most students is figuring out those combinations. But once you get that figured out, then and get the probability histogram or distribution, it's easy. Again, these numbers add up to what? 1. Okay, so you can tell you're right. Okay, I mean, if they all add up to 1, you probably did it right. Okay, so that's always a good thing to do before you do the expected value, is make sure that that added up to 1. All right, any questions? Does that make any sense? Okay, so let's go ahead and take a short break here, about 5 minutes, and then we'll kind of work with this thing in terms of how you do bets and money and stuff like that, and how we use expected value. Expected value. All right, so here's kind of the basic idea on this problem is, okay, you have a spinner. You don't need to draw a spinner. I just did that kind of so visually you can see what I'm talking about. So you have 6 numbers, 0 through 5 on there. Everything's equally likely on the spinner. And then you're going to do this. A player is going to basically say, tell the dealer or whatever, okay, I'm going to put my money on the 2. All right, and then he's going to spin the wheel, and either he's going to win some money or he's going to lose that dollar, like that. Okay, well, if the dealer spins the number that the player says, then you're going to get $4. You win $4. Okay, so this basically is going to go like this. When we put this together, we're going to kind of start with our random variable. The X is going to be the number that comes up on the spinner. Okay, whatever that is, okay? So there's 6 possibilities, okay? So you're either going to spin the wheel and you're either going to get a 0, a 1, a 2, a 3, a 4, or a 5. So those are the possible outcomes. The random variable is what number shows up on that then. Okay, now what we're going to do on this is we're going to do a payoff table on this, kind of like this. So let me show you how you put together this payoff table. All right, so it's going to go like this. The random variable, we have X like this, and this is going to be like you win $4, and then this would be like you lose. So that's going to be, we're going to put a negative number there because we're losing. So 4 is going to be positive, and that then, okay? So then we're going to do the probability like this, and we only got to do those 2 things. Okay, so here's how the game works. I say, okay, I predict we're going to get a 4. What's the probability of me getting a 4 on that spinner? 1 out of 6, right? Okay, the probability of any individual thing is 1 out of 6. Okay, all right. So the probability of winning this game is 1/6. What's the probability of losing? 5/6, right? Okay, so that's a 5/6 probability you're going to lose because it's going to end up on some other number like that. Okay, so what we're going to do is we're going to kind of see what happens with this expected value then. Okay, and I'll explain how this works in terms of betting. All right, so $4, 1/6 probability you win, 5/6 you lose. Now go ahead and do the expected value like we've been doing. So real easy, what you do is you do 4 times 1/6, use a positive number for 4 because it's a win, and then do plus -1 times 5/6 like that. You're losing $1, so it's use a negative there. Okay, so if you crunch this out, that goes straight across, that would be 4/6 plus -5 out of 6 like that. Okay, well, you can go to the calculator if you want to, or that would just be -1/6. So if you put that in, I think that would give you around 17 cents, if I'm thinking correctly here. So I'm just going to go -1 divided by 6. So my expected value ends up being negative. So we'll kind of talk about what that means. So in terms of money, that's about 17 cents. Okay, so here's what this means. In the long run, are you going to win money on this game or lose money on this game? You're going to lose. You know how much you're going to lose? If you played this game like a million times, you would probably end up losing 17 cents. That's what that means. So in the long run, you're going to lose 17 cents. Okay? Okay, now that's the way casinos operate. They want the expected value to be negative. They want to win more than you win. That's how they stay in business. So they could play with these numbers, 4 and 5 or whatever, and then they could adjust those numbers so that the expected value comes out in whatever favor they want. Okay, does that make sense to everybody? Okay, all right. Now, I'm going to do this same problem again, but I'm going to change the numbers around a little bit. Okay, so we're going to repeat this problem, but we're going to say you win 5 instead of 4, but you still lose 1. Okay, so let's do another payoff table on this problem, then I'll let you do the expected value. So this is all the same, except this time you're going to win $5 on your $1 bet, and you're going to lose $1. You lose your dollar bet if you lose. So this is still a 1/6 probability, and that's a 5/6 probability like that. So let's see what happens if we adjust the winning to $5. So let's go ahead and do the expected value on this then. So you do exactly the same thing. You do 5 times 1/6, then you do plus -1 times 5/6. So what you end up with is 5/6 plus -5/6. So what's the answer? Okay, what does that mean? You break even. Okay, so if you play that game a million times, you're probably not going to win, but you're not going to lose either. Okay, so what we call this a fair game. There's a branch of mathematics known as game theory. If a person's a math major, you can take a whole classes in game theory. So the idea is expected value is, if it's 0, just means it's fair. Okay, you win as much, you basically aren't going to win or lose money in the long run. So that's the idea. All right, does that make sense to everybody? Okay. Okay, so that's one of the things we use expected value for is to be able to crunch out betting and see how this stuff works. And odds makers know all about this stuff. All right, any questions? Okay, so fair game, you want to make sure you understand the fair game is when the expected value turns out to be 0. Okay, so a little bit more I want to do on this. On this next page, I'm going to go ahead and work out another one. This example, it's just something I put up there. It's kind of like this stuff is analogous to doing averages. When you're doing expected value, it's not much different than doing averages on test. I could even say, so like for instance, I don't remember what the average of test 2 was in this class, but you could think of the expected value as kind of like the average of the test scores in this class. Okay, I couldn't predict what it's going to be really, but you can think of it as analogous to an average. All right, so let's see. On this one, I would go down to this example and put this together. So this is another kind of situation. So you want to be able to put this together. Expected value is easy to do if I give you the table. Now we got to put this one together like this, and we're going to do a payoff table on this. Okay, so basically with this one, this problem says that you have, there's a bowl that's got 15 pennies in it, and then it has 10 dimes in it, and then it's got 25 quarters in it. Okay, now what we're going to do is just kind of look at the expected value on this. Now this is a game I would play. The game is reach into the bowl and pick a coin, and you get to keep whatever you picked. Okay, I like that game. That's to my advantage. I'm never going to lose any money on this game. So on the average, we're going to figure out how much money we would get on the average of all of these trials. Okay, so we'll kind of think about how that goes. So basically what we're going to do first of all is we're going to do this kind of like this. We're going to do the probability of winning a penny, so 1 cent. Okay, we've got to figure out the probability of reaching in the bowl and getting a penny. Well, how would you find the probability of getting a penny? There's 15 out of what? I think all those numbers add up to 50, don't they? So yeah, 15, 10, and 25 adds up to 50 coins. So you would have a 15 out of 50 probability. I'm going to go ahead and reduce these fractions as I go. You could bypass that if you wanted to. So that would end up giving a 3/10 probability. So 3 out of 10 times you're going to, on the average, you're going to get a penny. Okay. Now we're going to move on to the probability of getting a dime, which is worth 10 cents. So what's the probability of a dime? Yep, 10 out of 50. And you can reduce that fraction by 10. You can reduce in your head or your calculator if you want to. So 1 out of 5 times you could expect to get a dime. Okay, probability of a quarter, what's that? That's a half. Okay, there's 25 quarters, 50 coins. So that would be 1/2 like that then. Okay, so what we're going to do is we're going to kind of make a payoff table on this also. So there's no betting on this, it's just you always win. So your payoff table would basically go like this. Okay, there's 3 possibilities. So you can win 1 cent, or you can win 10 cents, or you can win 25 cents. And then you just do those individual probabilities like this. So the random variable is X, and then we're doing the individual probabilities. So the probability of getting a penny was 3/10. You could change that to a decimal if you wanted to. And then the probability of a dime was 1/5. And then the probability of a quarter was a half like that. Okay? So what we're going to do is when we crunch out the expected value, it's going to be some number that's going to average up the winnings we would get in the long run. So what we do with the expected value is we just usually write that as E of X, like I've been showing you. Then we do 0.01 times 3/10. Now, if you want to convert these to decimals, you could. Like that's 0.30, 1/5 is 0.20, and 1/2 is 0.50. So you can take your calculator and convert to decimals if you want to, which is what I'm going to do. So that's just 0.01 times 0.30 plus 0.10 times 0.20, and then do 0.25 times 0.50 like that. So that would be the average payoff from reaching in and grabbing a coin, okay? So let's see if I already did this. I ended up getting, I think, about 0.148. So I'm just going to round that to about 0.15. So in the long run, you'll win about 15 cents. Okay, now the reason that makes sense to me is because basically you have half of your coins are quarters, the other half are either pennies or dimes. So it's a little closer to the quarter. Okay, so it's a little bit closer. That's why, to me, that makes sense. Does that make sense to you? Okay, so on the average, you're going to win 15 cents. It doesn't mean you're going to win 15 cents because that's impossible. It means on the average, if you played this game a million times and averaged up all your earnings, it'd be about 15 cents. Okay, does that make sense, what I mean by that? Okay, that's what expected value is. Okay, sometimes students think it means I'm going to win 15 cents. No, that's impossible. That's the average of your winnings. Okay. Okay, so let's put this one kind of together here, and I'll kind of lead you through what you want to do on this. Then I want you to try to see if you can complete this. So this time you have these coins. You have 120 nickels. Okay, and a nickel, of course, is 5 cents. So your payoff table, you'll have X, P of X, and then 0.05, and you want to figure out the probability. And then you have 80 quarters. It's the same game, except you've got, I don't know why that says single coin. I think, yeah, okay, yeah, single coin. That makes sense. Okay, so that's going to be 25, okay? So go ahead and see if you can put this one together. It should just take you a minute to put that together. Figure out these things. You want to figure out the probability of getting a nickel, and then you want to figure out the probability of getting a quarter fill that in your table, and then crunch out the expected value. Okay, so how many coins are there? 200. Okay, and you don't have to reduce the fractions because you can do this all in your calculator anyway if you want to. So just see if you can get that put together. I would probably do my probabilities, just write them as decimals, and that would be kind of a simple way to get that put together then. And then your answer on this problem would be the kind of the average of your earnings. So it should be somewhere between a nickel and 25 cents. Your answer should be somewhere between 0.05 and 0.25. And just set it up and do it on your calculator. Anybody got anything? 13 cents. Anybody else got 13 cents? Okay, all right. So first thing you want to do is the probability. There's 200 coins. Okay, so the probability of getting a nickel, there's 120 out of 200. And I just took my calculator and did 120 divided by 200 to get 0.6. For quarters, there's 80 quarters out of 200. That's 0.4. Notice these two numbers, 0.6 and 0.4, add up to 1. So in your payoff table, you would have 0.6 there, 0.4 there, and then your expected value goes like this, like we've been doing. You just do 0.05 times 0.6, and you can do it all in one step on your calculator. And if you do that, I think I got 13 cents. Okay, so that's what you would get. Like I said, it's somewhere in the middle of 0.05 for the nickel and 0.25 for the quarter. Okay, that's the idea. You have more nickels. Okay, so that's why it's a little closer to that value of 0.05. Okay, so it's not halfway in the middle. All right, any questions about this then? Okay, that's what we call a payoff table. So you want to be able to work out those kind of things. I think this last page we're going to do a couple of more things with payoff tables, and that's pretty much what I'm going to look at in this section then. Okay, so let's see what we got on this example 8 here. So this says that you have 2 coins are flipped. Okay, and it says you win $2 if you either get 2 heads or 2 tails. And then it says you lose $3 if a head and tail turn up. So what's the expected value of the game? Okay. All right, so the first thing I'm going to do on this is I'm going to list all of the outcomes. Now, you don't have to do a tree diagram, but you can if you want to. I'm going to do a tree diagram. We have 2 coins flipped. So basically it would go like this. The first toss, you'd either get a head or you would get a tail. Then if you go to the second toss, you would either get a head or you would get a tail. So I'm only doing this tree diagram just so that we can list out all the possibilities on this then. All right, so how many possibilities are there? There are 4, okay? So the possibilities, or the sample space, which I usually represent by S, is just these possibilities. You could get a head and a head, a head and a tail and a head, or you could get a tail and a tail. Okay, since we're going to be doing probabilities, you need to figure out what the sample space is. You always need to do that, but you can do that in your head because it's pretty easy to do that small of a number in your head. Okay, so what we're going to do then is we're going to look at our random variable then. So basically it says you win if you get 2 heads or you get 2 tails. So you can write that out like that. So that basically would mean 2 heads would be the possibility HH or TT. Okay, so that the probability of getting 2 heads or 2 tails would be 2 out of 4. Okay, like that. So that's what that probability means like that. All right, so the probability of losing would be if you got what? If you got one of each, head, tail, or tail, head. Okay, so that's what that's saying. The game says you win $2 if 2 heads or 2 tails turn up, otherwise you lose. Okay, you with me so far? Okay, all right, let's see, payoff table. So now we're going to do this payoff table. Okay, so we got these possibilities like this. So when you do a payoff table, you just want to represent what your earnings are and what your losses are. So we kind of write this like this. So according to this problem, you're going to win $2 if what happens? If you get 2 heads or 2 tails. So what's the probability of getting either 2 heads or 2 tails? 1/2, right? Okay, 2/4 or 1/2. Okay, the loss, this problem says you lose $3 if you get either a head, tail, or tail, head. So what's the probability of losing on this problem? 1/2 also, right? Okay, so it's half for both ones. Okay, now we're going to see what the expected value is, and we'll see if this game is, if you're going to lose in the long run or win in the long run. So now what you do is once you got that payoff table done, then you do the expected value. So you would do $2 times 1/2. Now I'm just going to write these halves as decimals, 0.50. So I do 2 times 0.50 plus, then I do -3 times 0.50 like that. Well, again, you just do that on your calculator and you'll get a negative number. I can tell it's a negative number. So if you did that in one step on your calculator, you can check me on this. I think that's -0.5. Okay, so what it means is in the long run, you're going to lose, that would be 50 cents. 0.5 is half a dollar, so you would lose 50 cents, okay, because it's negative, okay? All right, so that game is not a fair game. You could kind of play with the numbers and figure out how to make it a fair game if you wanted to, okay, like that. Okay, does that make sense? Okay, the big deal is figuring out the payoff table, figure out the individual probabilities of the winning and the losing, and then doing the expected value is not that hard of a thing to do, okay? All right, any questions on that? Okay. All right, I'm going to look at this last example on here, and this is one more thing that I want to look at with this is with some data analysis on this. So let's see. I'm going to see if I remember what this problem is saying. Okay, it says after careful testing and analysis, an oil company is considered drilling in 2 different sites. Okay, it's estimated that site A will net $30 million if successful. And let's see, they will lose $3 million if not. And they're given these probabilities. So successful, you're going to win $30 million if it's, and that's a 0.2 probability of drilling and it's successful. Okay, then you're going to lose $3 million if it's not successful, and that probability is 0.8. So notice that one probability is 0.2, the other one's 0.8. Those two add up to 0.8. So that's side A. We're going to do actually 2 problems on this. Then we're going to do site B, okay? So we're going to start off by just kind of looking at the information on side A, okay? So this is kind of what they say on side A, okay? You have a 0.2 probability of winning $3 million. Okay, and I'm just going to put like, $30 million. You win $30 million, and that's a 20% chance. Okay, and then there's a 0.8 probability, and on that you would lose $3 million, like that. Okay, so you can do the expected value. You don't have to do a distribution table. You can do the expected value like this on this problem. So you just basically look at the win and the lose. So the win would be a 0.2 probability, and then that would be positive $30 million you bring in. Then it would be a 0.8 probability but then you would lose negative 3 million like that, okay? And then you could put that in your calculator, and that would tell you kind of what the expected value is. So I just do 0.2 times 30, and then I do plus 0.8 times negative 3, so that will end up giving me about 3.6. All right, so since it's a positive number, does that mean you're going to win money and be successful or lose most of the time? What'd you say? Okay, yeah, you're going to win. You're going to make money. You're going to be successful. So that's what you want, is in the long run, you would have enough successful drills that you would gain $3.6 million. Okay, now what we're going to do is we're going to compare that to the other site on this. So if we go to site B just basically says this. If you read about site B, it says you're going to net 70 million if you win, which is a 0.1 probability, and you're going to lose 44 million with a higher probability of 0.9. So on site B, the expected value would go like this. Okay, the probability of winning is 0.1. That's what the problem says. And then you're going to win $70 million. Okay, then it says you're going to lose $4 million, and that probability is 0.9. Okay, so you want to use a -4 when you do that like that. Okay, so it's the same idea. You just got to know what that information is giving you. So on this one, I just go, you can use your calculator, 0.1 times 70, and then plus 0.9 times -4, and let's see what happens on that one. Okay, so this one, it looks like you've got, hold on, is that, I put the wrong thing in. I lost the negative. So 0.1 times $70 million, and then plus 0.9 times -4. So you got to put the loss in a negative number like that. So that's 3.4. Okay, so which company are you working for, A or B? Or which site? Yeah, you want to go with A. Okay, so again, this one gains 3.4, so site A is a little better. Okay, so that's the idea. That's just kind of an illustration of how you can compare expected values on two things. Okay, so that's how that goes. Okay, so what do you guys think? Okay, expected value is not a hard thing to crunch out as long as you have the probability and whatever that value is. Payoff tables are the same way. Just have a probability of winning and a probability of losing, and then find the expected value. Okay, it's not that bad. It really isn't. Okay, any questions about what I just did? Okay.